Now let's move on to see some of the most fundamental engineering definitions and design practices that apply perfectly to aircraft design. And a good understanding of these principles will allow us to build a solid background, which will allow us to better understand everything that will come subsequently in this course. So it is very important to understand these things right here. So as we are mainly concerned with with designing an airframe structure, which is basically the skeleton of the airplane, the metal of the airplane, if you like, that is designed to take all of the flight loadings, and it gives the airplane its shape and delivers all of its promises regarding its performance, its efficiency, and all of things that are included in its design task. So the aircraft structural design is the process of creating a structure from an idea to its eventual recycling, right? So everything starts with an idea. Right? And that idea comes from basically a design task that is performed by a customer, right? So there is a customer. It can be, for example, an airline company, or let's say Ministry of Defense if it is in fighter, or if it is military aircraft. So someone needs an airplane that needs to have a certain set of characteristics, or a certain set of flight performance, a certain speed, a certain altitude, and a certain, for example, payload capability, a certain range, for example, right? And there's quite a lot of flight performance characteristics that could be mentioned here. And this idea is what we start with for designing an aircraft structure. So it gives us a shape. First, it gives us a geometry. And this geometry is going to give us the limits in which we can design the structure. And also it gives us flight loadings. So we have certain forces and moments that are acting on the surface of the aircraft, and therefore we're going to design a structure specifically to take those kind of loadings, right? And here, worth mentioning, as written here in this slide, it is the process that goes from the idea to its eventual recycling. So it has to do way more than just designing the structure by itself. So it has to do way more than just calculating the structure and doing all of the tasks that are required for designing it, manufacturing it, and so on. So it also has to do with the life cycle of it, right? So both the cost of design, research and development, design, and even during operation, for example, maintenance and so on, and removal from service. So all of those things that we have seen in the aviation complex are also included in the aircraft design structure. So when we design a structure, we design it not only to fly aircraft, but also to be able to be operatable, to be able to manufacture it, to be able to eventually even recycle it afterwards, after finishing its service, right? So it's quite a very big process, and in particular, it is a process of determination of the necessary set of structural elements, one that meets the requirements specified earlier during the general design of the aircraft, or during the design task, right? So we have to, so this process is usually choosing a certain set of structural elements, for example, set of spares and some other structural elements that are designed to take some specific types of loadings, and collectively assembling these elements together into a single framework that is going to work better inside of a geometry that is designed by aerodynamics. We're going to see this a little bit later. And next we have the next definition is called structural sizing. After we have an idea of which structural elements are going to be included in the airframe, it is the process of creation of specific design of a part assembly, airframe assembly, performed with cooperation between structural design and stress engineers. So this is quite a little bit advanced level of designing the structure. So when we know the structural elements that are going to be included in the structure, after that we have to size it. We have to define how much, for example, every structural element is going to be thicker, or how much its loading is going to be taken, and its strength margins, right? So this process is done by both stress engineers and design engineers. So design engineer designs something, and the stress engineer tells us whether it takes the loadings or it doesn't. If it does so, it does its job. That's perfect. If it doesn't, then the designer needs to make some changes in order to make the structure work, but at the same time get the minimum mass of the structure, right? So something that has to do with optimization, right? So you have to optimize the structure so that will work, but at the same time have the same minimum mass, and that's also quite a very daunting task. Now, the structural design engineer is the person who creates an image of what he wants to design, first in his hand, first in his mind, then on a piece of paper or computer screen. if you like, and then which will subsequently be refined in iterational process, and only one final version will be further materialized using manufacturing technologies. And what could be said here is that the process is extremely iterational, right? So it's not very always straightforward, clear what the best decisions are, right? So for example, you can try one design decision and then you can find out that it doesn't work, and then you can change some inputs and make the process in another iteration and so on. And here the imagination and the experience of the designer is very important in terms of finding the right decisions where you can change the design so that it's going to work better, and always going to be lighter, always going to have a better performance of the aircraft in the end of the day. Now, an airplane can be defined as an aircraft heavier than air, designed to transport cargo, passengers, payload, and so on within the airspace, using the aerodynamic lift of wind and equipped with an engine for thrust. We're going to see a little bit later other flight principles that include, for example, the buoyancy, the reactive flight principle. So an airplane is heavier than aircraft, that is, it uses the aerodynamic flight principle. That means that it uses aerodynamic lift, and therefore it is equipped with a lifting surface, which is called the wing, right? And aircraft structure, or the airframe, is set of load-bearing structural joining elements and fasteners designed to withstand all types of loadings acting on the aircraft under every external condition arising during aircraft operation, right? Basically during the aircraft flight. So here pretty much everything is clear. We're going to see other types of flying vehicles other than airplanes, so that we're going to understand the place of the airplane and the general picture a little bit later. So a part is a product made of homogeneous material without use of any assembly operation. So it's made of kind of a single piece of material, if you like. So without any fasteners, without any assembly operations, without welding, without any kind of assembly operations, right? So it's just a single piece material. Just if we take one piece of material and machine it, or having its shape made just to be one single piece, so that's going to be a part of the airframe. And a part usually a single piece, like here, sheet metal profile or complex shaped machine part, is designed to take loadings as part of a node structure, right? A node or an assembly structure, right? And a node or assembly is a set of several parts, assembly units connected together to perform specific types of tasks within the structure of an aircraft unit. For example, a wing spare assembly or a wing panel assembly. So as you can see, the spare assembly or the panel assembly is a part of the wing, which is a unit. We're going to see the definition of a unit here, right? And a unit is a framework of parts and assemblies. So it is kind of the biggest assembly level of inside of the aircraft's airframe. It is defined as so to perform a specific function in the structure of an aircraft as a whole. So in general, so it's like a global function, if you like. So for example, the fuselage, the wing are units. Why? Because the wing, for example, performs a global function which is generating lift, and the fuselage performs a global function that is housing the payload and all of the other systems, right? So, and these units include a lot of nodes and assemblies, which they themselves are made of a lot of parts, right? So this is the lowest level, the medium level, and the general level of assembling the airframe structure into units, and then we have the single framework, which is called the aircraft airframe, right? So units are made of thousands and thousands of part joints with fasteners, rivets into sub-assemblies, which together form bigger assemblies, and eventually a large unit, such as a wing, takes shape and performs a very large and global function in the aircraft as a whole. Now we can move on to see some of the design practices or axioms or best practices that are used in fact, most of the general engineering, mechanical engineering, if you like, not only aviation, but they work perfectly in aviation. That's why it is something that we have to take into account when we're going to further learn other parts of this course. So the axiom number one is with the same initial data, so the inputs with the same inputs A, B, C, so with the same design task, if you like. So for example, if the design task is the customer wants an aircraft that has a certain flight performance level, for example, each designer will have his own design. So fully identical designs never occur, unless this is an exact copy of another designer's work, of course, so this is cheating. Why this is the case, it is because the number of inputs is limited. So we have, for example, certain flight performance, while the number of outputs is basically unlimited. And so, for example, there are quite a lot of solutions that we can make, and all of these solutions, they can work the same way. For example, we have certain type of, let's say, structural loading on the wing, and every structural designer can come up with a different structure, and all of those structures work perfectly to take the same loading, right? So we have the same input, but the output depends on the designer and on its experience, on its objective perception of the aircraft and so on, and also on his own imagination and intuition and so on, right? So the process is extremely iterative, and it's extremely imaginative, and it requires way more than just performing some calculations or some routine tasks, right? So it's very iterative work. And so in this regard, as you can see here, for example, we have quite a lot of airplanes that have pretty much the same aircraft performance. So the flight speed, for example, flight altitude, and other aircraft performance is pretty much the same. All of these aircraft here, they have the same kind of level of performance, but every aircraft looks pretty much the same, and at the same time very different from the other aircrafts, right? And this is only from the outer skin. If you get inside of the structure, you find literally 1,000 differences, right? But that's because every designer has his own experience, has his own intuition, and he comes up with different solutions from other designers, right? Now let's see the axiom number 2 here is also another example of where the aircraft is very similar only from outside, right? Why? Because the physics of flight is pretty much objective, right? So it's not subjective. It doesn't depend on the designer. Here the design task is basically the same. So the design task is designing a supersonic bomber, right? And these two bombers designed in two different countries, they ended up being very similar only from outside. Why? Because the flight physics is pretty much objective, so the atmosphere is the same, if you like, and because the task is the same, so the outside geometry is the same. But if you get inside the structure, you'll find that these aircraft are very different in terms of the structural elements. The materials are different. Everything is very different. The philosophy of design itself is pretty much very different. Now, the axiom number 2 is that if the designer doesn't have enough data for further work, then he is always allowed to assume or guess the values of the missing variables. If, for example, we need more data than available, which is the case, of course, when we start designing something from scratch, for instance, or even not from scratch, there's always something missing in the beginning. And based on the design experience, intuition, and statistics, we can assume something and later on correct it during the iterative process. So although the term guess may not sound very scientific, so it's kind of a little bit informal notion, of course, but indeed it has long been used in scientific empirical method, right? Where we start from guessing a law of nature that we don't know how we don't have quite a lot of information about, and then make experiments to see if our guess complies with what happens in the real world. If it does so, it becomes a fact. So it becomes a well-known fact. So it becomes a law of nature. Right? If it complies with what happens in the real world, and if it doesn't, that means it's wrong, right? And therefore it needs to be corrected. So our guess has been wrong. We have to correct it, and in order to achieve a better guess, and then a better guess will lead us to even a better guess, and finally we're going to come back. We're going to get into an objective truth, which is going to be a law which will work in real world nature, right? So in engineering design, it works pretty much the same way. The starting point, at the starting phase, we usually know only so little about the design, and in order to continue the work, if we don't know something, we assume its value based on, again, experience, intuition, and statistics. So there are certain aircraft that has been designed before. They have certain flight performance. They have certain design practices that has been used before, and we know this works. So we are going to start from those basic things, and then we're going to develop our own design, of course. And later on, these values often get corrected in an iterative process. So we have to repeat this process again and again and again. And the more data becomes available, the more precision is acquired, and the less iterations are going to be left for further achieving the work. Now, the last axiom here, or best practice, if you like, in aircraft design is sounds as follows. Variable values of initial data roughly assumed by the designer do only impact the number of iterations. And the end result, however, is determined by the designer as a result of analysis of the available options. Let me explain what this is, actually means. So no matter how bad our guess was, right? So we can guess something that is very far away from nature, especially if we design, for example, something from scratch, and we know very little about everything that has to do with this designed objects, right? So we can start very far away from the truth. And the thing is that no matter how bad our guess was, the final result is going to be always the same, and it impacts only the number of iterations, right? So if our guess was pretty much good, so then only in few iterations we can get to the final result. But if we, for example, our guess was pretty much very bad, then we're going to take a little more time to get into what really means, right? So that means that more iterations are required, and the more far away from truth the initial guess was. And however, we don't really need to keep infinitely increasing the precision of values that we are going to be calculating. Rather than that, what the last sentence here, determined by the designer as a result of analysis of available options, means actually that rather than continuing to refine the results infinitely, the designer makes a decision on the suitability of an option as long as it becomes useful for further steps, right? So if we, for example, we can use the data, we decide that it is useful, that means that this is enough. So we don't have to, for example, keep improving the accuracy of calculations and so on. So we can move on to other steps of design. So, and it's worth mentioning here that in engineering, a widely accepted level of error or margin of error is about 5%. Right? So if, for example, our guess is within 5%, then that means this is acceptable for engineering purposes. And any fault of increasing the precision beyond 5% is usually regarded as a waste of time, right? So we have to move on to do other tasks.